Marco Perez is joining us. He works at the Modal Shop, which is a few-hour drive from me. And they are, is it a subdivision or a sub? They're owned by PCB, who makes the standard impact hammers that many of us use, and accelerometers and microphones. And one of the things that didn't work for me with the PCBs were their power supplies. They seemed to be ill-designed and hard to use. And then Marco came along and really came up with, I thought, the best interface I've ever seen. Hold it up now, Marco, if you have it there. It's a tiny little thing with the AD conversion. Oh, that's the old one. Yeah, and that one you have to
That's the old one. That's the one when you know,
you have to screw off the back.
That was designed by the company founder in the 60s. So
okay. Well, I called the company once to ask about it, and they said no, they weren't going to update it because it wasn't worth it.
But this is the new one that it's much more interesting because it's we'll talk about during the presentation, but it's USB power and it has 2 channels. And it's much easier to use as plug and play. And
right, there's no sound card you need. There's no volume controls to get out. I think you nailed it. So anyway, you start. Thank you for joining us.
Well, first of all, I mean, thank you very much. I mean, it's an honor to be here in being part of this community, which I'm getting to know a little bit, and I will, without any more delays, jump into my presentation, share my screen, and then I have a slide where I introduce myself. Okay, oops, did that go? No, okay, here's the PowerPoint. I'm being recorded, okay. Can you all see me there?
Yep.
All right, so just keep yourself muted, but you can interrupt me anytime if you have a question or a comment, or just to help me get out of trouble. So today, what I wanted to do is just to share a little bit of the sensors and the instruments that we use when we are dealing with essentially sound and vibration and structural testing. And this products and these sensors are used in a variety of applications, including musical instruments. So I'm gonna attempt to give a quick overview here and discuss a little bit what you guys been using since I learned from Joseph, his rig and his violin test rig and setup. So we're going to discuss that a little bit and go through the details of some of the sensors and the instrumentation we use for that. We've got a quick agenda there. We're going to talk about what is a sensor, what is a transducer, some of the common types that are used for this kind of musical instrument measurements. Talk a little bit about calibration, data acquisition, and questions and answers. I was told 40 minutes about the time for this presentation, so we'll try to keep it around 40 minutes, maybe a little longer, depending how it goes. And as Joseph mentioned, the whole thing started with PCB, Piezotronics in the late 60s. The company, this is our sister company, mother company in Buffalo, New York. And like any other good American company, it started in the basement of one of the founders. The 2 founders were 2 brothers, and they started PCB in the late 60s with the vision of building better sensors that were easier to use. And the company's been around to this date. And we are about 1,500 employees worldwide and all over the world. We have offices in China, Italy, France, UK, you name it. In other countries where we don't have an office, we typically have a sales office with a distributor. And company is pretty big and pretty vertical as we build almost everything that we do in-house. There's a huge machine shop in our headquarters in Depew, New York, outside of Buffalo. And if you ever go to Niagara Falls, you're more than welcome. Give me a call. I will hook you up with my colleagues there, and you can get a nice tour through the facilities and see how the sensors are made. And the sensors, like I mentioned, they are used in a variety of applications, from industrial applications where you do machine monitoring for vibration, in the aerospace and defense industry, in the automotive industry, and so on. And, moving back a little south here in Cincinnati, where it's starting to snow, and we're gonna expect a lot of snow this weekend, I've been told. One of the family members, the son of one of the founders, came to Cincinnati to study, and he started the company about 35 years ago. Outside of, he went to the University of Cincinnati and never finished his master's, but started the company. The company is being here, where we deal with several products that gravitate around the sensors. Different applications related to vibration testing, to digital sensors. We also have a rental service program where you can rent any of the sensors that PCB makes. So if you have a quick test and you want to experiment or try a new sensor, you can get those from us. And we also do calibration systems where we calibrate the sensors that PCB manufactures. And talking a little bit about me, I grew up in Brazil, and went to the University of São Paulo, one of the largest cities in South America. And some years later, I got a master's degree from Purdue, not far from Cincinnati. Purdue is in West Lafayette, Indiana. And I started with the model shop in 2005. It's gonna be 20 years in October, hard to believe. And so you can notice a little bit of an accent when I talk. I always joke, this is my Ohio accent, and with a little bit of Brazilian accent, you could say. And my relationship with music is through the Brazilian music, where I play the acoustic guitar. But in the classical music world, one of my good friends from college went to engineering college with me, and he's probably watching the presentation as we speak. He's a violin player. So throughout college, I was lucky enough to go to all his concerts downtown São Paulo for free. He always had some extra tickets. He would give me some tickets, and I watched all sorts of concerts, and my friend playing on stage. And he now lives in Ann Arbor, coincidentally, and he's a doctor and specializes in radiology. So if you ever need to X-ray a violin, I'll hook you up with him. I don't know if he will do it, but at least he can ask the guys at the hospital to see if they have an MRI machine, and we can scan some violins for you guys. So a lot of what I do has to do with helping customers deal with different applications and problem solving and some testing needs, and trying to connect them with some of the products that we manufacture, we sell. And so I typically deal with people like anywhere from the aircraft manufacturers to satellite companies that putting satellites into space, to people making consumer products or medical product devices. And once in a while, I get a call from somebody who wants to test a musical instrument. So that's quite interesting. It's a little bit outside my area of expertise, and it's quite interesting because it's a little bit of the opposite. Usually most of the people I talk to, they are trying to control noise. They're trying to mitigate sound, isolate vibration, and things have resonances, as and you're trying to control those or change or shift how things vibrate or how things sound. in the musical instrument world, it's a little bit of different, right? You want to enhance the sound. You want to perhaps, resonance is a good thing, a lot of times. You want to get that sound amplified. You want to make sure you understand how things vibrate and how you can replicate the sound and the feeling of the instrument you're playing. And it's a quite interesting area because again, sound is very subjective, right? So if you want to say, okay, how does it sound? Does it sound good or does it sound bad? Or it's very subjective. You can ask different people, you get different opinions. If I ask Joseph, he makes good violins. Everybody knows that, but it's his baby, right? You're gonna ask him, is it good or not? I mean, of course, his answer is gonna be biased. And so, how can you find ways to basically quantify things, and that's where measuring the instruments comes into play, right? You want to find ways to get a repeatable and an objective assessment of that particular object that you are talking about, right? For whatever reason, right? You want perhaps to create a mathematical or analytical model of the instrument so you can play with different materials or different geometries or different designs. You perhaps want to do a quality control if you're a manufacturer like Taylor Guitar on the picture there, and you make hundreds of guitars and you want to make sure you get a consistent manufacturing output. So there are different reasons for measuring the musical instruments, and you guys know that even much better than I do. I try for this presentation to prepare myself, and so I did a tour to my basement and I found all these great books that I collected over the years that talk about acoustics and that talk about musical instruments, and I truly recommend especially the first two books. The first book is from Thomas Rossi. He passed. He was a professor at in Illinois, Northern Illinois University, I believe. And he is a terrific professor. The way he writes and explains things are very easy to read. This book, The Science of Sound, is very non-mathematical. Anyone can read it. He has an even better book with another professor where he goes a little deeper into musical instruments. The second book is a book from the 50s, from Olson. Harry Olson was one of the pioneers in the audio industry. And this book is like it's so cheap, you can buy the paperback copy of it on Amazon or any other bookstore. And it's a beautiful book with lots of information about musical instruments and just instruments in general and music. The last book is a professor from Purdue University. He wrote like 3 books about acoustic guitars, and again, I'm just mentioning that because those are interesting literature that I happen to have, and I was preparing for this presentation, and I never finished the presentation until the last minute because I started rereading or reading the books, and I got really fascinated by all the information that's available out there. And last but not least, I think you guys have done a tremendous job with the YouTube website, the Oberlin Acoustic Workshop. I started watching some of the videos there, and I felt quite intimidated, like what I'm going to talk about today. After you guys, it looks like you already talk about everything. So, all right, let's go back and talk a little bit into the sensors. Those little guys. You see here in the middle of the screen. And I also had, I don't know if I can show, okay, I'll show you later. I had a picture here on the sensor, but they are really small, really tiny. And let's see if I can just transition to stop share for a second. And this is like one of the accelerometers that we use to measure vibration on a musical instrument. So it's the size of a fingernail. You want that to be as lightweight as possible. And here's the little hammer that Joseph uses on his testing rig. It's about we call it a pencil hammer because it's the size of a pencil. So we have those little sensors here on the table. Maybe if we have time, I can give a demonstration at the end. So far, so good. Am I talking too fast, or is that everybody can hear me? Okay, let's share the screen again. All right. Okay. All right. So my first slide here is, what is exactly a transducer, right? So a transducer is a technical name for any device that can convert some type of energy from one format into another, typically from some type of mechanical energy like force or vibration into an electrical signal, or vice versa. So when you refer to a sensor like an accelerometer or a microphone, so basically an accelerometer, you're inputting vibration in the form of acceleration and converting that into an electrical signal. If it's a microphone, you have a sound wave, and that sound wave, once it hits the microphone outputs an electrical signal that's proportional to the amplitude of that sound wave. If a transducer can also be an actuator, where you're doing the opposite, the other way around, right? You're applying an input signal into a device and creating some kind of a mechanical motion or vibration. For example, a shaker, a vibrator, or an actuator. You have a driving signal, could be like a sine wave, and then it goes through an electrodynamic or an electromagnetic device like a shaker or a speaker, and that translates that into a sound wave or a vibratory or oscillatory motion. So that's in the particular case of an accelerometer, you're measuring acceleration, but there are different ways to measure vibration. Vibration can be expressed in terms of velocity, displacement, or acceleration. And there are different sensors for measuring vibration. You could use like a laser Doppler vibrometer. That is another way to measure vibration in terms of velocity. But anyway, in all these cases, all these different sensors, one thing that's very key is calibration, because calibration is a way to provide a physical meaning to that sensor output, to that electrical output, because an electrical output is a waveform. It's like it's volts over time. That change in the output of the sensor. What does that mean in terms of physical quantities? How many newtons of force am I measuring? How many pascals of sound pressure, or how many meters per second squared, or G's of acceleration am I measuring? So that meaning is given to the sensor through the calibration process. And whenever you're selecting a sensor, you're going to test a telescope that you're sending to space, or you're going to test a violin, or you're going to test a piano. You have to consider several factors before you pick the right sensor for that measurement. So you have to know a little bit about the system you're trying to measure up front, right? And that will help you select the sensor type and the technology. And even more important, what kind of amplitudes are you expecting? If I'm measuring a car that I'm driving on a rough road, of course, it's going to vibrate way more if I'm driving a car in a highway. The frequency of interest, especially when you're talking about musical instruments, different musical instruments have different frequencies that they can produce. the sensitivity of the sensor, how sensitive is the sensor, right? Is if you're measuring things that are very, very, very small, you need a sensor that's very sensitive. If you're measuring things that are really, really big, like an explosion or a shock or an impact, you need things that are not as sensitive because you don't want to saturate or overload the sensors you're using. So all those things are things that, you know, when I'm talking to different people and helping different people with different applications, those are the questions and things I'm trying to understand so I can better help my customers, my clients. When it comes to measuring vibration, you know, usually the sensors, they measure vibration in one direction. You have sensors that are 3 sensors in one that can measure vibration in 3 directions, X, Y, and Z. Microphones are a little different. They're typically omnidirectional. You can get sound waves coming from different angles. And there's a lot more things that we won't be able to talk here today, like, you know, mounting, how you power the sensor. But we'll make sure we talk about calibration and a little bit about powering, because that's where the whole idea of making it simple and easier to measure the instrument comes from. So the different sensor types, you know, depending what kind of sensor you're talking about, you know, in our company, we manufacture a lot of piezoelectric sensors, and we can use the piezoelectric property of crystals, such as quartz or man-made ceramic, to measure acceleration, to measure force, to measure pressure, to measure strain. There are other technologies out there. For example, you could have capacitive sensors where basically the sensor is a capacitor, and a microphone is a good example of a capacitive sensor where, you know, once the sound wave hits the microphone membrane, you know, it basically disturbs that capacitor gap and generates a voltage output. So starting with the microphone, that everybody knows what a microphone is, and I'm using a microphone right now to talk to you guys. But what we're going to talk about today is like a measurement microphone. What is that? How is that different from the microphone you have on your laptop computer, on your cell phone? Again, it's the whole idea is if I'm designing a microphone to put on my telephone, you know, the main application for that microphone is to capture voice, right? So as long as the microphone can grab and acquire, you know, the sound of my voice within a limited frequency range, everything is fine. And because I'm talking, there's a language element, so you don't really need this to be a very accurate microphone, because our brain will do the job to connect the words and create a meaning of what I'm saying right now. But in a lab, what we want from a measurement microphone, we want something that to be as neutral as possible. You know, something that behaves the same way today and tomorrow. Something that I can measure, you know, a bass or a violin or a drum, and I can measure different frequencies, and it gives me the same response at different frequencies. So for that reason, you know, these microphones are very different from what you see on consumer products and what you see in the audio world when people are recording music, for example. If I'm recording my voice, I'm singing, you know, of course, if the microphone makes my voice sound better, that's fine, you know, no problem. But if I'm recording something like something that makes noise, and that noise annoys people, or that noise, it's a factory floor, and people are exposed to that, and that can cause hearing loss, that kind of thing. You want to be able to really quantify what you're measuring. And microphones don't live alone. They always go together with a preamplifier, and the preamplifier does the trick to make the electronics of the cartridge, which is the sensor itself, compatible with whatever you're connecting the microphone to. So what we call condenser microphones or precision condenser microphones, they are standardized. So that's one of the first differences between this kind of category of microphones and other microphones out there. And this is something, you know, the type of microphones we're talking about here, what you see on the screen right now probably came out in the 50s, even before that. But since the 50s, the microphones, they got pretty much the shape and size that you get right now. And the IEC 61094, it's an international standard that basically, there are several standards within that standard that talks about the construction of those microphones, the different type of frequency response, especially the size, right? You know, the typical microphone we use on a variety of applications are half-inch microphones. There are also microphones that are 1 inch, a quarter of an inch, and 1/8 of an inch. And having that standardized, it's a 13.2 millimeters plus or minus 0.03. Having that standardized allow us to check the microphones really easy, to calibrate them. And of course, you know, you want to cover the hearing range typically, but there are microphones that go beyond what we can hear, you know, to measure ultrasound or infrasound. And there are microphones that can measure super, super quiet sounds, or microphones can measure super, super high amplitude sounds. And again, you want those microphones to be reliable, consistent, and the word we use very frequently, flat, right? You want them to be flat across the frequency range. The way they work, it's pretty easy. You have a protection grid inside that. You have the diaphragm, which is a very thin metal membrane, and it is one side of the capacitor, and the back plate is the other side of the capacitor. And usually that black plate is polarized or pre-polarized. You know, in the past, you would apply like a 200 volts to that back plate. Nowadays, you can also have pre-polarized black back plate, where you put a coating of a special material and you polarize that material, and it stays like that. And just a little animation there. So as the sound waves hit the diaphragm vibrates and basically changes that distance between the one side of the capacitor and the other side of the capacitor, which creates a voltage change. That voltage change fluctuation is proportional to the sound pressure level, you know, to the intensity of that sound wave. And we are talking about really, really, really minuscule movements here. An analogy that somebody made is like, we're talking about, I think, nanometers. So think about this microphone as a 1/2 inch diameter. And the amount of movement that it's exaggerated on the animation, if the microphone was the size, the diameter of planet Earth, you know, you would have that membrane moving up and down about 5 meters. So that's how little that moves. And that change in the gap is proportional to the sound pressure level. And that's why we want to make sure that is true, you know, and to do that, we take the microphone to the laboratory. We provide the microphone with a known sound pressure level. You know, one way to do that is to use a piston phone, which is the little thing on the left, little instrument, little calibrator on the left. And once you know the output of the microphone, the electrical output, and you know the input, which is provided by the piston phone, you run a frequency response using what's called an electrostatic actuator. So the electrostatic actuator basically simulates a sound wave within different frequencies, and then you can basically sweep and measure the microphone output all the way to the highest frequency that particular microphone can possibly measure. And last but not least, you know, you generate a calibration certificate that basically tells you this microphone is flat, this microphone behaves the same way at different frequencies. And you can do the same exercise at different amplitudes as well to make sure the microphone is also linear across different amplitudes. And again, this is all standardized. You know, people have spent decades coming up with methods and ways to test those microphones. It's not just like, I am PCB, I calibrate my microphones one way. I am, Joe Mo across the street and I calibrate my microphone in a different way. We all follow the same recipe, the same standard. But not everything is the same, because when you try to collect data from a microphone, just in terms like just looking at the condenser microphones, you could have different electronics and different ways to handle the what we call the signal conditioning. So when you starting from the microphone, you have the preamplifier, you have some cabling, you have the power supply or the signal conditioner, and last but not least, you have your readout instrument. Could be a PC, could be a oscilloscope. So in this picture, you see three different ways to basically handle the same microphone. One is using an externally polarized one is to use 200 volts polarization voltage provided from the signal conditioner. The second one is using a pre-polarized preamplifier. And the third one is probably the one you're more familiar with, is like using a phantom powered microphone system. So they all work with the same microphone in this case. So anyway, not gonna get into much detail here, but the whole idea is how can we keep it simpler, right? Is there maybe an easy way to handle the microphone, the hammer, the accelerometer, all the same way? So that's where I'm trying to get to. So moving on from the microphone, let's get into the piezoelectric world where the little hammer and the accelerometers are. So the word piezoelectric, I forgot now, but I think comes from the Greek. Piezo means when you squeeze, you squeeze a crystal and that generate a charge output. And the easy way to think about it is like this next animation, right? Think about the crystal is like a sponge, right? You have a wet sponge, and when you squeeze a sponge, you get some water that comes out of it. And here's the same thing. You squeeze that crystal. That crystal could be a natural piezoelectric crystal like a quartz or a tourmaline. It could be a man-made crystal where basically we go to the lab and we have this little secret recipe where we manufacture the piezoelectric material. But one way or another, it works the same way. When you apply a force or a pressure into that material, it generates a charge or a voltage. I can amplify that charge into a voltage. And this kind of technology measures dynamic signals, meaning signals that change over time. So it's really ideal for vibration, for sound, for pressure, things that fluctuate over time. You won't measure like a static pressure. If you inflate a balloon and you leave it there and the pressure doesn't change, you won't be able to measure with a piezoelectric sensor. But if the balloon is blowing and the air is coming out, then you can measure that fluctuation. And so you will use the same principle to design different sensors. So if I'm designing an accelerometer, the way we do that, we use what's called a seismic mass. So we have this little tiny mass that sits on top of the crystal. And as the accelerometer moves up and down, basically that mass pressure applies a pressure over the crystal and creates an electrical output. If I take a larger picture here and I cut the sensor in half, you would see there are different designs and different configurations. But one thing I want to highlight on the sensor on the right here, in this case, the crystal is sitting sitting around a pole, and you have a ring. And that ring is a seismic mass that goes up and down, and it basically is not putting pressure on the crystal, but it's trying to shear the crystal, and that also creates a charge output. Don't worry too much about that, the construction, but the only thing to remember is just you're squeezing the crystal, and you can design sensors like the one in the middle where you have basically 3 sensors in one case, and that enables you to measure X, Y, and Z vibration in all different directions. The other thing you see on this picture is hard to tell. Let's see, I don't know if I have a pencil, but I can't find it. So we'll use the cursor here. So you can see a little circuit board on top of the accelerometer, and that is like a preamplifier. It also helps you, transform the signal from a charge to an electrical, low impedance electrical signal that's easier to measure and easy to make it compatible to the electronics out there. So again, when you're picking up an accelerometer, you want to make sure you have the accelerometer that can have enough sensitivity to measure the vibration, that has a frequency response that's broad enough. There are things like the amplitude, make sure it measures low amplitudes as well as high amplitudes and so on. But I'm not going to get into too much detail, but again, every one of those accelerometers are calibrated, and the calibration again goes back to a particular standard. We go to the lab and we are always calibrating the sensor we don't know against a sensor that we know. So it's always like a chicken and egg game when you do we call it a secondary calibration. Ultimately, you calibrate the accelerometer against a laser, which is a primary measurement, because the wavelength of light doesn't, the speed of light doesn't change. So if you know the laser, you have a primary way to measure the vibration of the accelerometer. And then once you calibrate that one, that becomes your reference. You use that reference to calibrate the next accelerometer, right? So we do that in the lab. There are standards that teach you how to do that. And you can do that for different frequencies, for different amplitudes, and at different temperatures. And a typical accelerometer will put out 10 millivolts or 100 millivolts per G, where G is the acceleration of gravity, 10 meters per second square approximately. And what you're gonna get a number. This number, 10 millivolts per G, is exactly the electrical output as a function of a mechanical input. So what we typically do in the lab, we put the accelerometer on a shaker. We know that shaker is vibrating at 1 G or 10 Gs, and we measure the output of the sensor. We do the math, we plot the graph on the right, and that's your certificate that the accelerometer is, again, flat. That accelerometer will not introduce any kind of color or bias into your measurement. The accelerometer has a particular frequency response that is specified. So usually, you want to make sure that accelerometer covers the frequency of interest you're trying to measure. A lot of times it does. When it comes to high frequencies, it may be a little tricky. And just in general, there's always a trade-off. If you want to have an accelerometer that's very sensitive, you need more crystal, or you need a better crystal with a higher output. So usually a high sensitivity accelerometer will be larger, but because it's larger, you also lose some frequency range. So if you want to measure real high frequencies, you need a smaller accelerometer. So you got to find, so that's kind of our constant battle, trying to get the best compromise of having an accelerometer that's small enough and still sensitive enough to do the measurement. And then the hammers, right? When we're talking about the instrument hammers that we are using to test the musical instrument, the impact testing technique is it's used in many different areas. So I found lots of pictures on the web. I wish I could give credit to everybody, but I couldn't. I really did a bad job here. But I was able to give credit to some people. So there's a nice website from Dr. Dan Russell from Penn State. He has lots of acoustic animations and some testing results there, some including violins. And he's done modal testing on a beer bottle, on a hockey stick, on a little fan. People use very large hammers to test foundations and bridges, or even like there's a little wing, air wing here for wind power. You can test machine tools, you can test disk drives, you can test guitars, violins, airplanes. So it's a very popular technique, you know, in our industry. And PCB has been doing hammers for a long time. You know, we even had a patent on it, you know, where we did some magic in the hammer to make it more rigid and get a better performance across the different frequencies. But the bottom line with hammers, you know, they're manually operated, they're easy to use, they're typically manually operated. We'll talk about that in a second. They're portable, fast. You don't need any elaborate fixturing, which is kind of the opposite. When I saw Joseph's setup, he did a really clever setting where he holds the hammer and he actuates the hammer using, I think it's a little solenoid, and that makes it very repeatable and very easy to do, because especially with the mini hammer, it's really hard to use that, operate that with your hand. And to get the repeatability that you want to have on the violin testing, you know, the fixturing that Joseph did it's really amazing. We have some electrical hammers that people use in our industry, especially for testing in production line, for doing quality control, people testing brake discs. And some of those electric hammers, you know, they cost thousands of dollars just for the automation, which, you know, Joseph did something similar for a much simpler way. He implemented that. And well, how does the impact testing works? And so basically the hammer produces a pulse, and that pulse will change depending on how hard is the hammer tip, and how soft or how hard is the what you are hitting. You know, how compliant is, if you hit a piece of metal is less compliant than if you hit a piece of wood or something that's more like a rubber. And you know, the harder the hit, you know, the wider the frequency range, so you can put energy. You're basically putting excitation into several different frequencies, and you can measure the output, you know, how the structure vibrates, how the musical instruments vibrates, and you can look at those peaks in the vibration response. You normalize that by dividing by the excitation input, and you get those peaks, and that's called the frequency response function. And those measurements, you know, they highlight some of the resonances that are present in the system. And that's really important because, you know, the different, I mean, if you have a string instrument, you know, the string creates the vibration. It has its own resonances, or, you know, basically you tune the string to a particular frequency, depending on if it's a viola or a violin or a guitar. It could be a D, an A. But, you know, the sound of the instrument gets amplified by the whole dynamics, structural dynamics of the instrument itself. And that's where, you know, you guys know more about it than I do. That's why what I was reading on the books, and it was fascinating, because you have the, you know, the front board, the back board of the instrument, and how they vibrate. You know, you have the different modes of vibration. That's the whole modal analysis area, where, you know, depending how those, you know, the front and back plate, if they vibrate in phase or out of phase. If they're out of phase, you have the breathing mode, usually one of the first modes. And then you have, you know, some bending modes, and all those modes of vibration, they correspond to the different peaks that you see on the frequency response function. And it's a signature. It's basically, it's a vibration signature of the structure under test, in this case, the musical instrument. Hammers are calibrated. We do the calibration using the tip of the hammer, since some hammers have different tips. And again, it's a comparison calibration, a ratio calibration. Remember, we just calibrated the accelerometer, so we use the calibrated accelerometer with a calibrated mass, and we hit that mass, F equals ma. We calculate the hammer sensitivity. and that is in the units of force. So that'll be in like millivolts per newtons or millivolts per pound force. So, okay, finally, I know it's been, maybe I'm a little over the time here. Let's talk about the instrumentation considerations. So when I first learned about the setup that Joseph created in his paper, I think it's one of his, I think the picture on the right is from his original paper. And I saw this, the little old, we call it the old blue box, those little very old-fashioned power supplies for the sensors. That's what powers the microphone, not the microphone, that's what powers the hammer. And for my surprise, Joseph had a microphone, and that microphone was powered by something else. It was a phantom powered microphone. It had its own box. So every sensor had its own box, and some of the sensors, they talk directly to the PC. Some of the sensors talk directly to something else. I don't remember. But when I look at that, I said, hey, this is pretty cool, I mean, a very nice application. But then you're using all these different things and cables everywhere. Perhaps, that was that was the way to do it, but not exactly the easier way. If you can use the latest and greatest technology that we have available now. So the idea is, you're using the accelerometers, you're using the hammer. Those sensors are what we call ICP sensors, and they are powered using a constant current diode and a voltage. And there's a whole class of sensors that are powered that same way, using a coaxial cable and a simple, connection, easy to use. A lot of the microphones out there, especially in the recording and audio industry, are phantom power, which is, it's a different scheme, where you have 24 volts and you have its own dedicated power supply. And those microphones, like I mentioned before, they may or may not necessarily be measurement microphones. They may not necessarily be calibrated. They may not be necessarily flat across the frequency range. So how can we kind of unify and consolidate everything? And I think that's what the setup was, Joseph, that I think you're connecting the output of the power supplies all into the little Octave something, the little microphone, the Roland power supply there, and you had the software that you guys developed. Anyway, it would be really nice if you could just take any sensor out there, at least the sensors we talked about, go through a little device and connect that to a computer. And again, you're using a PC with a software that was written in a language called LabVIEW. But somebody else may want to use MATLAB. Somebody else wants to use maybe Python, which is very popular these days. And that's what we came up some years ago, where basically we took advantage of the USB connectivity. USB has been around for a long time, and it's probably the most common interface available out there. And that made it really easy to make a device that was universal and that could talk to anybody, because PCs, they understand USB, they understand what we call USB audio, right? And that is also available on Android phones, on iPhones, and also on single board computers like Raspberry Pi computer. So we decided to make something that was really, really universal and easy to be connected to any different types of sensors within that category of ICP that I just mentioned. This device is, so sorry for the advertisement right now, but this device is called the DigiDAQ, is something that we sell. And it's not the only thing out there, by all means. I mean, there are other things that are available that can do, A to D, analog to digital conversion and acquire data. But what's kind of funny is that while a lot of the industry out there that I live on, people got really serious about data acquisition. The more is better. So you have systems out there that can measure, 8, 16, 32, hundreds of channels. And that's really necessary if you're testing an airplane or some large object, some large structures. But a lot of times, you measuring 1 or 2 channels, it's enough, and actually you can get tons of information. And really, the trick is how you interpret that information, right? Measuring, I would say, measuring is easy. The hard part is like, what do you do with that measurement? How do you really interpret that measurement? How do you make sense? This is the sound of a good instrument. So we can use that DigiDAQ device to connect any different types of sensors, even sensors that have a voltage output. We have an option for that. And that opens up, the possibilities. The picture there, I'm using my cell phone, and I'm measuring just the noise coming from my little compressor that I have at home. And I'm measuring the vibration of the compressor. I'm measuring the sound of that compressor. And if I was going to apply that to the violin, I just need to get the hammer and the microphone connected to each one of the channels there. And again, plug that into my device. And what I'm really getting out of our digitizer here is a data stream, right? We are not storing anything. We are not amplifying or equalizing. We're just getting raw data stream from the sensors into the computer or the phone. And it's up to the software, how you're going to look at that data. You're going to look at the spectrum, take an FFT, look at the frequencies, measure different points. But the idea is to have something simple, affordable, reliable, and calibrated, so you can take those measurements without too much complication. So some of the technical things behind it, because it's USB, you don't need a power supply. A USB does the powering. So that simplifies the connections. When I'm converting a sound wave into a digital format, I'm using a high sampling rate, so I can cover the frequency range up to 20 kilohertz, which is the hearing range for humans. I'm using a 24-bit A to D converter for the best digital resolution. Just of comparison, CDs are 16-bit and they're pretty good. So 24-bit, it's even better if you can tell the difference. We are not doing anything proprietary. We are actually using USB audio class 1. So that's kind of a native to the operating systems out there. So if you're using Microsoft Windows, if you're using Apple iOS, Linux, Android, doesn't matter. All these operating systems have native support for the audio drivers that you need. And that allows you basically to develop systems in whatever your favorite, if you want something totally portable, of course, a phone and a tablet is ideal. If you're in the lab, a PC is probably the preferable platform. And last but not least, it's easy to integrate. So when I first talked to Joseph, he said, hey, you need to talk to Chris Rogers at the university. Chris, he's a LabVIEW guru, and he can see if it was going to work or not. And I'm not a programmer myself. I did programming back in college. It's been a long time. So when I talked to Chris, I don't remember, but I talked to him one day, and like 2 days later, he already had his ObiApp up and running on this new platform. So for anyone who is more adventurous, we have code examples available. It's all free. It's all available for, anybody who wants to customize or write your own software. And in today's date, it's pretty fun because, I couldn't resist because I'm not a programmer. I thought, hey, can I use AI to write a program for me, and that was really mind blowing because, I took I have one of my colleagues here who is a programmer in the office, but he's always so busy and he never had time to help me out. So I did this thing with ChatGPT and I created some few lines of code, and I just emailed my buddy and say, hey, hey Tom, is it what do you think about it? And said, yes, Marco, that's a pretty good job. I mean, I would just change the sampling rate, but it works. And that was just to kind of prove on how easy it is to get started with something that's open format. And I never really realized the power of that, but this is really, once you have, in this case, I was trying to write something in MATLAB, but now everybody's using Python. So I said, okay, well, can you just translate that code from MATLAB to Python? And a few seconds later, the ChatGPT did that, rewrote the code into a Python language. And Python is popular because, again, it's free. That was the next question, how can I run a Python program? Because when I went to school, I learned Turbo Pascal, how old I am. So I had no idea. Then, one of our students here said, Marco, come on, and you just go to python.org and you download the Python compiler or whatever they call it. And I was up and running with Python on my computer, 20 minutes later, I could grab 2 or 4 seconds of data and plot that on the screen. So it's very powerful, empowering, to have those tools available, even if you are an advanced programmer. And last but not least, I promise I'm finishing. We talk about calibration, how important it is. And if you are adventuring and if you have an existing software, doesn't matter if it's a commercial software or something that you wrote, there are tools to check the sensors. We call them, portable calibrators or field calibrators. And depending, again, each tool for each individual sensor. So if you're doing a microphone, if you're using a microphone, we have this little sound source that's a 1 kilohertz, 94 dBs or 1 Pascal. If it's an accelerometer, we have a little handheld shaker that can create a 1 G of vibration. And once I turn the shaker on and I look on the screen and I see that peak at the same frequency that I expect and the amplitude, okay, everything is working. So it's not just calibrating, but just making sure everything is working, everything is repeatable. Now I can go and I can measure my violin, do the measurements. After I'm done with the measurement, I check the system again using the calibrators and make sure everything still behaves the same. So it's a pretty good common practice when you're doing measurements. All right, so I just want to wrap up and emphasize that having laboratory grade instruments and sensors, it's really key to get accurate, reliable, and repeatable measurements. And you need that because so you can objectively describe that instrument that you have on your hand versus, okay, hey, if you have like me, I have a friend that plays the violin, and okay, I can just give to him and maybe, hey, what do you think? But again, it's going to be subjective, and you want to have something that's objective. And all that system, it's much easier and much more accessible to use as before. 10, 20 years ago, you would probably spend way more money. It would be way more complicated and less accessible to get your hands on this kind of instrumentation. And the instrumentation can be checked in the field as well as periodically checked in a calibration lab. So, and again, you don't, if you like Apple or you use a Mac, you can do all your things in a Mac. If you like a Windows PC, you can do your things on a PC. Or if you want to develop something dedicated and use a Raspberry Pi computer, you can do that as well. It's not as complicated as it used to be. And that's what I wanted to share today. And thank you very much for your patience. I hope everybody's still there. And if you are there, please say hello. Let me know if you have any questions.
Thank you so much, Marco. Any questions? Fan, do you want to take over the moderating? You're muted.
Oh, okay, I've unmuted myself. If you have questions, please use the if you can the raise hands feature. And if you can't find it, you can always type something into the chat.
Well, let me start with a couple of comments. Well, thank you so much, Marco. There are well, a few simple questions that I think I was talking to Jim about. He was wondering, with your little accelerometer, can you tap it with a hammer? Will that damage it?
No, it will not. But in practice, we avoid tapping directly on the accelerometer because the accelerometer itself is a piece of metal. It has a case, and that case, you're probably you may risk saturate the accelerometer because you're gonna get too much amplitude directly on the accelerometer. And the other thing is, again, it's better to tap near the accelerometer, as near as possible. So you're not really exciting. The accelerometer has the bottom of it is where it's calibrated, and that's the surface that's designed to give you the best measurement, right? So that's just as, you want to avoid that.
So if you're trying to do like a drive point admittance, so it's really hard. Doing it near it on a violin is not doing it. But you're saying as long as you don't tap it hard enough to saturate it, or perhaps use a soft tip or a soft cover, you're not going to do any harm.
You're not going to do any harm. But again, like I said, I mean, it's you may be causing, you may be creating, introducing some error in your measurement. Because the accelerometer expects vibration in the bottom surface, which is where you're mounting it.
Oh, I see. So you're creating.
So to give you an idea, for example, this accelerometer that I have on my hand happens to be aluminum. And we have accelerometers that are made of titanium, but aluminum is not as rigid as titanium, for example. So if you're hitting with the hammer on the accelerometer, you may end up creating like a ding, and squeezing, because the bottom of the accelerometer is rigid enough but not the top necessarily. The way the accelerometer is constructed, if I go back to one of the slides, I think you can see that. Hold on just 1 second. If you go back to the cutaway, right? So if you look at this accelerometer on the left or on the right, the top of the accelerometer is basically a hollow. It's an empty can, and the bottom of the accelerometer is built as a rigid base, right? So this particular accelerometer you see on the screen, if I'm hitting on the top, it's like hitting a drum. Right.
Okay.
And
so you'd want to, maybe perhaps you could stick a thick rigid surface on, or indeed build a bridge over it so you could be in the same location but not
right.
lighting the top.
A lot of times what we do, if we have that luxury, not always available, but if you have, let's say, a beam, and you're hitting one side of the beam and the accelerometer is on the other side. So sometimes you can do that, and you can approximate those two sensors are on the same location. And
Jim was thinking, okay, so your tiny accelerometer has a round part and then a rectangular part. Is the center of measurement at the center of that circle? I guess it shouldn't matter if everything's moving in plane, but is there a particular point where, well, Jim, you're there. Do you want to ask that question better?
Yeah, shall I chip in on this? Just a reaction on your previous comment. I think what you're telling us to do is that if we absolutely have to tap on the accelerometer, we should glue it onto the structure upside down,
That's a great idea.
because that won't make all that much difference to the sensing ability, but it would give you the base. We're always doing this kind of thing with those 0.3 gram, your smallest, the smallest of the small
0.3 gram.
accelerometers, which maybe don't have much of a can around them, in fact.
Good idea. That's brilliant.
But what was your question? You asked something.
The center of, well, it's one you asked.
Yes,
the
yes.
center of
So
measurement.
for the measurements up, so something I've been involved with Joseph with in just recently, it turns out that a millimeter or two movement makes a difference to the thing we're trying to measure. And so that makes it really important to know where exactly is the line of action of the measurement of the accelerometer to the millimeter. Do you, is that, that's an interesting question.
I think, a few things are important. I mean, one is consistency, right? Whatever you can do is what you can do. If you want to stay consistent with the method that you're using. Anytime you're measuring something in the lab, I mean, there's always an approximation of the real world, and you try to keep it as consistent and repeatable as possible. Sometimes, it does make a difference. Then you have to find a different method. We have accelerometers that are much bigger, unfortunately, but they are designed to basically, I mount the accelerometer on one side and it measures on the other side. And we use those accelerometers for calibration purposes as a reference accelerometer. On the little tiny accelerometers, I would say it's something, I could go back to my colleagues and look at how is the internal design of it. Or what you could do is to try to do it, try to measure and tapping on it and measure real close to it, see how much difference you get.
It's nice to,
That's what we've done, really. I mean, I'm putting you on the spot here with there are very few applications where a millimeter of movement makes a difference. We happen to have been dealing with one of those, and we've done what you said. We tried it.
But wouldn't it be good to know where in the structure is the crystal that's moving? Just so you know
the effective line of action. If you want super accurate measurements, then any sensor will have an effective line of action, which doesn't appear in the data sheets. So just something to feedback. Just occasionally, fussy clients like us may not have any money, but we're fussy about details. It would be really nice to know if those calibration measurements have been done, where on the footprint of the sensor the prime sensitivity is.
Well,
where
the calibration, the measured sensitivity, when we do the calibration, it's right at the mounting of the accelerometer.
But whereabouts in the footprint? Sorry, I shouldn't hog the discussion here. We're putting you on the spot with something.
No, but that's a good question. I mean, we have many times where people take an accelerometer and they mount it upside down.
Yeah.
Right, and depending on what kind of sensor you have, if you mount it upside down, you get different results. And the reason being the fact that one side of the accelerometer is designed to be the mounting surface, and the other side is not. So you have to pay attention to which side is the mounting surface, and that not only is the most rigid part of the accelerometer. To avoid, there's a problem when you're designing an accelerometer called base strain. You try to minimize, you build an accelerometer to minimize the base strain, which is basically like a ghost ghost output due to the strain on the bass. You try to minimize that when you design an accelerometer. Plus, that's the face, that mounting surface of the accelerometer is right in perfect contact with the mounting surface of the reference accelerometer, which is the one that's used to calibrate it. So that is the most accurate measuring point for the accelerometer.
And if you mount it upside down, does that change the phase? Does that make any, does that need to be
If you mount
accounted
it
for?
upside down, yes, it definitely changed the phase by 180 degrees. But the worse than that is not necessarily where the sensor was calibrated to begin with.
I'm
So-
assuming that if everything is moving in a plane, that wouldn't matter. Of course, if there's any motion that way, it would. Is that
No, it's changing the phase because there is a convention, right? If it goes up, it's a positive.
Ah, okay.
If it goes down, it's negative. So if you flip it, now you basically change the phase by 180 degrees, or which again, do you care about phase or not, depending on the application. Typically, when you're doing an FRF, you do care about phase. You want to measure several different points, perhaps, and you kind of want to reproduce the mode shapes, then you do need phase.
Okay. Luca, you've been had your hand up a while.
Yes. Sorry, you can't really see me very well. I'm dark in here. Thank you very much for this great presentation and very thought-inspiring for me. I'm working on a very simple setup in the workshop to just be able to do any measurements at all. And your point about calibration, kind of, you said to relate the measurement to a physical property, calibration is a prerequisite, of course, but I want to highlight that a lot of measurements that we do not require an actual physical measurement. So oftentimes we're not interested in how many newtons of force did I put in, how many pascals of sound pressure came out. I'm just interested in, is A bigger than B? I'm comparing two instruments, let's say, and I just want to see, is the sound output of instrument A bigger than B, or is it lower? I'm not actually interested in the absolute values. So I think there are a lot of applications, especially in our field, I think, where calibration is much less important than like in general engineering fields.
You are absolutely right. There's a lot of applications where you're comparing, two devices, two products, and is it louder or how much louder, especially when you're dealing like consumer products, right? Maybe you're a company and you manufacture hair dryers or blenders, and you made changes in the design, you measure again, did it get better, did it get worse? And I totally agree with you. Calibration is also, I think, important in a way that it's a risk. How do you say? Calibration is also about risk mitigation, right? If I'm sending a satellite to space and I got $1 million satellite and I only have one chance to send it to space, right? And I want to make sure the satellite will survive the launching to space, and I want to test the satellite beforehand. I want to absolutely make sure I'm not over testing or testing too hard that satellite or testing too low, right? So there are situations where you absolutely want to make sure you cannot take any risk. And the other thing is for legal reasons. Somebody comes to you and question you, and say, hey, you're making too much. Your neighbor comes to you and say, you're making too much noise. You had a party last night. And how much noise is too much noise, right? It depends on, the legislation and of your city or your country. But anyway, and so that's one thing. There are times where comparison is enough. And there are times you need to know to precisely quantify. But also, a lot of times believe it or not, when I talk to people all the time, and because of the kind of job that I have, people always call me when they have a problem, right? And they call me, and our internal joke at PCB is, Marco, the microphone is not working, right? I'm not measuring anything. I can't get any sound. I know. I mean, my violin is making sound, and I can't see anything, right? Again, it could be the microphone, it could be the cable, it could be something on my software that's not right. It could be a bug in Windows. So having the field calibration, the field check it's a great tool to just a sanity check, everything is working in your test setup, in your measurement system.
Yeah,
So
definitely. I agree with everything you said.
Yeah,
Um,
Luca, and there's another important point, which is that um, while in a lot of cases, an absolute calibration may not be required, um, if you're comparing A to B, um, there may be a large time difference between A and B, and Murphy's Law comes into play, and there could all sorts of things could intervene so that what you think your measurement conditions at A versus time B may not be the same, even though.
yeah.
And I think for a lot of what we do, that's probably the most important aspect of calibration.
Yeah, I agree. And I think that's what I wanted to say as well. There is a middle ground between like an absolute calibration where I know how many newtons are there and no
Yeah.
calibration at all. I can also do just a calibration to an object that I have, I guess. I do a measurement that I know the conditions of with a given object, let's say, and calibrate to the response of that object that I expect. And if I can repeat that, calibrate, let's say, two setups or something, two measurement setups to give me the same result for this object, I still don't know anything about the physical facts, but I know that I will get the same measurement from these two setups. And if I have an object that is relatively stable in time, let's say it's a piece of metal or something that doesn't really change over time too much and is stored under good conditions, I can also do a long time calibration of sorts with that. So there's middle grounds for, I
Yeah.
think in the workshop, some easier methods are needed a lot of the time. So there are easier methods available than doing an absolute calibration every time.
Well, Marco, you touched on something. I'm guilty as one of the people who's called up, oh, it's not working, not microphones. Okay, so microphones and accelerometers, you can just test by putting them on different equipment. But with the USB sound card that you've developed, it's not so obvious. Because, and this was one of the first things I learned, was that Windows will intervene and start enhancing it or doing a bunch of things. And so you get it out of the box, you plug it in, it doesn't work. And you have to go through a bunch of layers to turn off the sound enhancement. So Marco told me that. Then another time it didn't work and I sent it back. I don't know whether you ever found anything was actually wrong, or I have one now. I've got two of them that belong to the OB Foundation now. One of them works fine. One of them won't work at all with my computer. It works on Luca's computer. Is there a way of troubleshooting them? There's nothing you can plug it into to say what it is. Any suggestions there about debugging that sort of thing would be great.
All right. Well, I'd say 90% of the time things work. The problem is like when they don't work.
Yes, yes.
We have experienced things where, we designed the product to be easy, right? And to be universal and to be able to talk to any device out there. And then I think I gave an example. If you're trying to work with an Apple phone, an iPhone, the iPhones are made by Apple and they control the design. It's always the same thing, right? And it typically, it's much easier to develop a software or an app if you're using the iPhone environment, the iOS environment. When it comes to an Android phone, Samsung, Motorola, Google, everybody wants to change a few things here and there to make it easier. Or Zoom, right? We're talking on Zoom right now. And one time I was I was presenting something and I wanted to show, oh, here's my hair dryer. See how much noise it makes. And nobody heard anything on the other side because Zoom has an active cancellation filter that totally canceled my demonstration. It was like terrible. So there are things that we don't have total control, which are, they put that filter for a good reason in the Zoom software, but that thing really creates trouble to me. One thing that we found out the hard way hitting our head against the wall was there was this Intel sound enhancement thing that was probably created for, during COVID and people doing all these different conference calls like we're doing now. And there was this Intel enhancement thing, and that thing totally screwed up our system. And it was basically a driver. And I keep telling people, you don't need any driver. You just plug it in. If I plug my device right now, let's see what I can. Let me try that real demonstration here real quick. I'm gonna plug that into my computer. So if I plug it right now, hopefully what I want to have is the original USB Microsoft driver, the one that Bill Gates wrote when he was still in college, and that's what I want. I don't want anything that Intel or Samsung or somebody else did later on trying to improve. I just need something that gives me the raw data without any filtering whatsoever. And that's where most of the problems we found where people had trouble using the device came out. The other thing is, if you look at my device right now on the camera, I don't know if you can, let me try again, see if the camera will show. If you look at the device, there should be a green LED there that shows the power.
Yeah.
Right? But if I'm not using the device after, I don't know, 30 seconds or a minute, depending what computer I have, the Windows may want to save battery and just turn that off. And things like that are tricky, and sometimes you have to hack into the settings of the computer and say, do not enhance the audio, do not save battery, just keep it on and don't mess with it. And that's kind of, the beauty and the challenge of, using a standard device like a USB device.
Yeah. So Marco, I want to sort of divide those problems into sort of roughly two areas,
Okay.
with these non-standard setups. One is, as we talked about, is it doing, is it not working, and et cetera, et cetera. But then there's another class of problems where it superficially is working. You get a signal. How do you know the amplitudes are actually the same as before? Because, for example, perhaps the Windows audio driver has changed the level control. Okay, so is there, and I think this follows up one of the questions perhaps in the chat. I don't know exactly what Joseph Chen is asking, because he says, how are the sensors calibration done? Because you did give an overview of the general idea of how it's done at the beginning, but that's with calibration devices. How expensive are those devices? Is there a fairly inexpensive way to ensure that your amplitude levels are the way you think they should be?
Okay. Yeah, so the one thing that it's very different from, like in the past, we would power the sensor and output a voltage, and we try to get that voltage into the sound card in the computer. And the sound card, that can be very tricky because, like you said, you can change the volume, the gain on the sound card, and you have a totally different amplitude, right? And you can do that during the recording, you can do that during the playback if you're analyzing and that kind of thing, we got rid of it, because now I'm taking the sound or the vibration and I'm digitizing that, into the device, right? And the DigiDAQ device itself, it's calibrated, right? And it puts out a number, okay? And that number we call a count. That number is proportional to the sensor you're measuring, or to the voltage that the device is reading. So then it is what it is. It's not something you can mess it up with.
So by using your DigiDAQ device, you've bypassed a whole host of potential problems because you're just putting out a number directly into the software.
Right. And that avoids what Joseph mentioned, back in his original system. He had the little Roland power supply, and that had a gain knob on it. And he would go grab a coffee, he would come back and somebody changed the knob, and then you never know where the knob position really is, and that can change things completely. Now this time you're not changing anything when you are acquiring data or recording data. Then the other thing is, like I mentioned, the field check. If you do have access, and I always recommend people, if you have access to a calibrator, to a field calibrator, those are pretty reliable, devices. And you just, you take the microphone, put the calibrator on, press the button. Do I read 94 dB? Yes, no. If I don't read 94 dB, something is wrong.
What's the approximate cost of those things? Are those fairly affordable?
You get them for $70 on Amazon. You can get them secondhand. You can get, and you can pay a few $100s and get them new.
Right. I don't know. Again, there are different ones. The ones that we sell, I would say they are not cheap, but I think they are. You pay a fair price for them. Let me see what I don't know if we have that price online. Let's see. So this is one example. There's no price.
Is that the Larson one?
That's the Larson one.
Yeah, I think it was a few $100s.
I think it's probably between $500 and $1,000.
Okay, so they're not more expensive than the sensors.
They are. They could be more expensive than the sensor. Let's see if I can find the price here on my. Why I can't find the price? Okay, sorry about that. I'm gonna.
No, I'm just assuming, like, decades ago, some of these calibrators were very, very expensive, and
no, I'll say they are, they are not. And again, the calibrator is also calibrated. So you go back all the kind of, the traceability, the whole measurement chain. We calibrate the calibrator using some traceable equipment. And again, it's all go back to the trust, right? You want to make sure you're getting how much worth is your time. You just measure, you just spend an hour measuring an instrument and how much the instrument cost. And again, it all depends, right? A lot of times, like Lucas said, you don't need that. You're making a relative measurement. And as long as you're not measuring today, whereas, warm outside, and you're measuring tomorrow and it's snowing and things have changed completely. But if you're measuring things and they are very comparable, about the same timing, and then, great. You don't have to worry too much, but then you gotta do your final check, right? And or maybe you're making hundreds of instruments, like if you're like a manufacturer that mass produce instruments. So anyway, is the risk mitigation, right? What's the risk of making a bad product, or having just it's an investment which I think it's worthwhile. Especially if you're measuring sound. Microphones are more fragile in general than compared to accelerometers. Well, the other easy thing is, like, have an extra sensor. Then you don't, if you say this microphone, I don't know if it's working, right? Maybe you have a second one that's your gold microphone, you only use that in special occasions, and you know that one is your trustworthy microphone. So you know, I've seen people handling that in different ways.
Let me just add something there. Both Jim and Evan have recommended to me after I've been digging into calibrators, and I've got a collection of them now. You really want to be interested in calibrating the whole system more than the individual components. And
Right.
Luca touched on something. Imagine we hang something like a carbon fiber plate where the violin would be. It's always going to make about the same amount of noise. Just put it in your system, get the measurement. Is it approximately what it did last time? Then you'll know your knobs are about right. Or the great thing about your unit is you'd get rid of a whole chain of knobs, plugs, and things. So yeah, I think calibrating the whole thing. For example, if one had a tube that's closed at one end and had the microphone plugged in the other, like a microphone calibrator, but you tapped one end with a hammer, then you could kind of calibrate those two together, and rather the way that George Stepani does with a mass accelerometer. You know, there's some, I think maybe some easier ways of doing it that would actually apply to our method.
Yeah, there are many ways. I'm not sharing the screen right now, am I?
No.
No, not yet.
Okay, let me see if I can find a microphone. Let's see if I can find something. Yeah, okay, I found it. Let me share my screen for a second here. Where are you guys? Share. So I'm here on our website, but you know, there are some devices like this little guy here, this 9917. I mean, this is just a little speaker. There's a speaker on the, and then I have two holes on this thing where I put a microphone on one side, a microphone on the other side, right? And it's just a simple comparison. You know, I have an acoustic, you know, cavity, and you exposing the two microphones to the same sound. So that's another way, you know, by comparing to something else. So you could use something as simple as like, you know, again, I mean, I don't recommend, but if you have like just a little speaker, right? And you have two accelerometers there, you know, one that is your trustworthy, your reference, and the other one is the one that you have questions about. You know, you would expect them to see the same vibration if they are mounted at the same location or close enough. So as a sanity check, there are many different ways you can check your system. The one method that's the most popular one and the less reliable one is to tap on the accelerometer, right? You have people or tapping on the microphone, right? That's, you know, you tap on and you hear, usually you get a very loud or very high level output out of it, and it doesn't tell you much. But when you have something like a sound source or a speaker, then you can change the frequencies and you can check different scenarios, and you know, it's a little bit better. And there's like a handful of devices out there. You know, this is the one device that's easy and low cost. We have a more expensive device that you can do all the way to 20 kilohertz. And if you're just doing like a single frequency, we have that little sound source that I mentioned before, the Cal 200.
All right. So Colin has his hand up. Colin? Are you there, Colin? You're muted.
There's also a couple of questions on the chat window.
Okay. Let's go to Colin since yes, I can hear you now.
Can you hear me?
Yes.
Okay, because my video has gone astray, and but that's no matter. Lovely talk. Really, I'm really interested. I was particularly interested in, of course, the pre-polarized condenser microphones that you produce, Marco.
Yes.
Do you produce that in a size that's small enough to get through the F-holes? The F-holes are about 5 millimeters in width.
Okay. 5 millimeters. That's small, huh?
Yeah.
Well, the short answer is no, because the microphones are 1/2 inch, which are 12 millimeters,
Right.
and you said 5 millimeters, right?
Tight fit.
So we don't have anything small enough like that. We have a probe microphone. That's the thing that as small as it can go to. So you don't have access to the inside of the instrument, do you?
No, that's if you're doing measurements on a real instrument, the only access you have is through the F-holes if you want to do measurements of the sound inside, which is
Okay.
what I'm particularly interested in, because of a direct relationship between the sound inside the instrument and the radiated sound. It's the sort of measurements I do, and it's particularly easy to do with little
Right.
electric. I use little electric microphones, which, you know, as you cost virtually nothing, and they have they have the advantage too of having an internal amplifier, which means that you can put them straight into an audio system, and I have a separate constant gain amplifier before it goes into the computer. So so it operates without being distorted by any of the windows sort of things, and it's constant gain.
Gotcha.
So it was very useful. I mean, and surely that there must be many. When you do, what happens when people put microphones on bats and things like that? Because and listen to the sounds they make, and they must be very small as well. But if you don't make a small microphone like that,
Well, the smallest measurement microphones out there are 1/8 of an inch.
yeah.
And we don't make those, so let's see, let's see, 1 divided by 8, it's a 1.125, and that is what?
Eighth of an inch is small.
2.5 millimeters, something like that.
That's 3 millimeters.
Yes, exactly. Exactly.
So, yeah, so you could use a 1/8 of an inch microphone to go through the F hole. So those microphones, our company does not make those, but there is a Graz and B&K. Those are two Danish manufacturers. They make those microphones.
Yeah. But
We may have some of those microphones here in case somebody wants to rent. We may have those available, but they are not made by PCB. But they're good microphones. The other way would be to use a probe microphone. And a probe microphone is basically the microphone stays outside, but you have a probe, like a tubing, that
Yeah.
goes inside the cavity or
Yeah.
inside the instrument. Have you seen those?
no, I know of people that have used them. Yes.
Does
Yeah.
that introduce resonances of the tube? How did they get away?
It does introduce-
That's
it-
the, this
it
is kind of the
introduces
probe
phase,
microphone that I'm talking about. And I guess we advertise that for high temperature applications where the high temperature would damage the microphone. But this is basically the microphone stays outside and you have this little tubing that goes inside.
Oh, I see.
And how does that interfere with the sound has always been a mystery for me. But the higher the frequency, of course, the higher the influence of
Yes,
that
exactly.
tubing.
Yeah. Yeah.
And that's what I think, that's what that graph shows here on the pressure response tested at different probe. Well, this is the length of the probe tip. So there's the length of the probe tip that interferes with the output. But again, it's a compromise, but it's one option.
Yeah. Well,
Is it
like Luca, I am particularly interested in changes. that one can make on a violin to know what their important function is.
Okay.
And that's important for the maker as well. And I personally find that the very inexpensive little electric microphones that cost less than a cup of coffee actually work extremely well for that purpose.
Yeah,
But on the other hand, I can well see that if people start off with the sort of low-grade microphone, which still works and is reproducible from day to day, and is reproducible in measurements for less than 1 dB. Once one has that, one could actually, if one really wants to know what's happening at high frequencies, there's a great advantage in having a microphone that actually has a fairly flat response, well above, shall we say, 2 to 3 kilohertz.
As I understand it, the trade-off between small microphone size, you have the great advantage of you can measure flat way up to the first resonance of the diaphragm, which is very high with a small microphone, but the signal to noise ratio is rather low. So you want a big diaphragm for that, hence the 1-inch ones. I think the half-inch one is a good compromise if you're measuring outside the violin where the levels are lower. And it's great if it can fit into a standard calibrator. Just so you can check things. Did I say anything wrong there, Marco?
No, you're right. I mean, it's a compromise. The smaller microphones are less sensitive. So your signal to noise will be not as good. And then you also have I mean, on the other hand, it can measure higher frequencies than the typical larger microphone.
And
yes, but the point is that the sound inside a violin is very focused, and therefore, whereas the radiated sound, you wouldn't use them for the radiated sound, but that the small size is actually not a great disadvantage for measurements inside the instrument because of the small volume the sound is actually going into. So
yeah, I think you have the right tool for your job, Colin.
Yeah, I think I do. Yeah.
And
Sorry, can I just add here? So just to add to the discussion, I've done probe microphone measurements, actually using a PCB probe microphone in the violin. I went through the end button. I had a hole drilled through the end button, and then the probe microphone fit through there. That works fine. It's I don't know if it's the most useful application, because if you already have a high-end microphone like that, you probably also have a lab and you can do measurements outside of the instrument. But talking about the electret microphones, I'm working with those as well. And I've recently done a radiation measurement with the electret microphones, and I actually get pretty much the same result as with the PCB equipment. So it gets very, very close. And I don't, just looking at the result, I don't really see a downside. So it's really indistinguishable, basically, the result, which was a big surprise to me. But I would say it's useful for that, even just having tried it. It looks pretty much the same.
The one thing about electric mics is that I believe they lose their polarization, so your effective sensitivity is changing.
They're over the long term, they're nowhere near as stable as the yeah.
Yep, definitely.
And well, let me just put in my 2 bits about whether to spend money or not. The PCB stuff is expensive. Especially when I started, and most violin makers don't have a lot of money to spend, especially on something they are not convinced is going to be useful in the workshop. So I started doing the rig or getting interested maybe 20 years ago, longer, 25 years ago. And there's a very different range of things available. The prosumer, so-called audio, was starting to burgeon. You started to get digital sound cards for $25 that, you remember Fan back, one of the original ones we had, you plug it in. They worked really well. And you can get a $25 microphone. Anyway, you can get impressive looking graphs. And it's really over time you want to trust your measurements more. You want to be able to compare them more. You want to get rid of some of the wires. And if you're like me and you're interested in tweaking equipment rather than just adapting to it, which is probably the saner thing to do. But it's actually, I would say when Marco introduced his USB, for the first time, I would say it became more cost effective to use PCB stuff for high level measurements than a collection of other things, because the Octacapture, $600, why use that one rather than the cheaper one? Because it has digital gain, so you can set it. If the number stays the same, you have the same gain, and so on. But then you have a power supply for that, and so you've got all these wires and things, and you end up spending something close with Marco's is roughly 1,000. The microphone is roughly 1,000. The hammer is roughly 1,000. I mean, give and take, so you're spending 3,000. We ask players to pay that for a not top end new bow, these are lifetime tools. I mean, the hammer I've had for 20, 30 years now, it's completely problem free. Same with microphones, and same I think with Marco's card. Once you can get through all the little glitches in software, so it does make sense to me, and it's so transparent when you can see all the parts. Trying to see what's wrong when you've got a maze of wires going everywhere, it's just hard. And one of the problems we had at Oberlin, the last live one, was a button got pressed accidentally to do with adding phantom power to a hammer, which it didn't want, or something like that. And yes. So what you need to do then is start building guards over things, and it gets more and more complicated. So I would call the mic, the PCB microphone, Marco's card, and the accelerometer a really solid investment. Not to say something better won't come along, and God knows Tom's working on a hammer that seems like it'll be really good, but I don't think you can go wrong with it. And to bring it back to Marco, the service that PCB offers is really great. I mean, I can call him up or send him an email and they will respond. It's not the same if you're dealing with Roland or Behringer microphones. I mean, they could care less what we're doing. I don't want to push anyone into spending money they don't have. It's always worth starting with the cheapest thing you can afford and getting going. But if you're thinking of putting time into it, and time's the biggest commodity, then it is worth it.
Yeah, Joseph, I was going to comment on that because, what I tell people is that the most valuable thing that you're going to spend on is your time. So you have to consider how much time are you willing to invest in doing this, and it's not for everyone. But if you're willing to invest significant amounts of time, in making measurements, then the amount of time you spend will be far greater than any amount of money you will spend. So you might as well, invest the money on reliable equipment. And the case in point was at Oberlin in the summer of 2023. Didn't we run around trying to find out how come we got a 2 dB discrepancy or something in the measurements from before?
Exactly. Evan found it was the phantom power button got pressed, which was putting it into the hammer where it should never have been. And fortunately, we could back that out because it gave a consistent rise. But
yeah. Okay, so Hans Johansson has a question. So Hans?
Yeah, thank you very much, Marco. Great talk.
Thanks.
I have a quick question. I have been using PCB hammers and accelerometers for mostly probably 20 years, and I've had I've had two hammers already. But I was wondering the calibration numerals that you get with the equipment when you get it, how reliable are they? Or maybe to make it a more precise question, how do those calibration numbers, how do they do in time as time passes? I'm talking not microphones, just accelerometers and hammers.
Right. That's a good question. So just generally speaking, any calibration that you do, if if you're sending your sensor to a calibration laboratory, and you can send to the manufacturer, we have a laboratory, we calibrate as a service. You can send to just a general laboratory out there, but any reliable calibration laboratory, one thing that we do is are you accredited? Being an accredited laboratory means, again, there's an ISO 17025 standard where you as a lab, you follow good practices, you don't drink while you're calibrating your sensor, but most important is the calibration is a measurement, right? And like any measurement, there is what we call in metrology an uncertainty, right? So when I tell you this sensor or this hammer here, measures 10 millivolts per Newton, and that has an uncertainty associated. Is it exactly 10? No, it could be 10.1, it could be 9.9, right? I know there's a probability of, there's 95% that this hammer gives you, 10 millivolts per Newton plus or minus 2%, right?
Maybe my question is, maybe to be more concise, is what are the effects, like hygroscopic, atmospheric effect? What is it that changes that calibration once it's there already?
Right. So that depends on the type of sensor, and I would have to look at the specific sensor you have. But one thing we do for accelerometers in particular, we know if the accelerometer uses a quartz crystal. Quartz as a nature-made crystal, it's extremely stable.
Right, I would think.
We have sensors that we calibrated for the last 30 years. And we not only us calibrating, but we take that same sensor, we send to the National Metrology Lab in Germany and PTB, and they calibrate it. Then we send to NIST here in the US, and they calibrate it. And we send to Inmetro in Brazil, and they calibrate it. So we have this sensor that is like we've been following for the last 30 years and measure how stable that sensor is, and it's extremely stable. It never changes.
Okay,
right?
It's both for the accelerometer and for the hammer.
But for example, that's because the sensor is made of quartz.
Right.
If I have a sensor that is made with a man-made ceramic.
Yeah.
Man-made ceramic is that crystal becomes piezoelectric. It goes through a process where I apply a high voltage on it, and I pull the molecules inside the crystal to become piezo. And that kind of a material will lose its properties over time, depending on temperature fluctuation, depending on shock, if somebody hit that sensor too hard. So there are things that can affect the performance of that sensor over time. And that will be, that could cause degradation of the performance of the sensor.
Okay.
So generally speaking, if you really want to trust your sensor 100%, what most people do in our industry, they take the sensor once a year, send it to the lab, get a stamp, get a new fresh calibration, and you say, oh my gosh, it was the same thing as last time, and I just spent $100, and that's what people do.
So the 0.2 gram accelerometers that the PCB ones that most of us are using, and also the smaller hammer sensors, are they ceramic or are they quartz? Or
that'll be on the specification for the sensor. Okay. For the accelerometer, I'm almost positive 100% the accelerometer is not quartz. Those little tiny accelerometers, they have to be made out of ceramic,
Okay.
because
Yeah.
the output of a ceramic crystal is much higher than the output of a quartz.
Right.
For the hammer, you don't necessarily need a high output because you're heating. You got a high level shock anyway, and I think the hammers are made of quartz. So I would say just guessing here, I would say the hammer would be more stable over time than the accelerometer. And what some people do, if you talk to big companies that have hundreds of accelerometers, or, they look at that kind of stuff and they say, hey, this sensor here is very stable. I'm going to calibrate every 2 years instead of every year, And you see people trying to define their recalibration interval based on how stable the sensor is and also how often you use, right? If you have the sensor in a drawer for the whole year, you never use it, I mean, nothing's going to change.
Right. Okay, thanks a lot.
On the other hand, I think it was the Larson microphone calibrator I got, and it said this should be calibrated every year. So if the calibrator has to be calibrated, then we're lost.
Yeah, again, the ISO 17025, we cannot dictate how often you recalibrate. It's your decision as a user. But on average, most people calibrate once a year.
Okay, thanks a lot.
Just like you change the oil in your car once every 3 months, You get a new prescription glasses every, I don't know how old you, depending how old you are.
Okay, are there any other questions? Because Luca, because I have a list of questions.
Yeah. Yeah, I think it's a question that many of us might have had at some point. The little hammer that we use, it comes also with different grips, I'm gonna call them. There's like a metal grip, I think it's made of aluminum, and a plastic grip.
Yes.
Yeah.
And of course you wonder, okay, these must have different vibration properties. Doesn't that influence the result? Like my answer to that was always, the sensor is not sensitive to the vibration properties of its handle. And that's why we can use very different handles with it. I know Joseph puts his hammers on self-made handles and doesn't affect the outcome. So could you talk to that? And then there's 2 calibration values that you get, whether or not you use the metal handle or the plastic handle. That's probably just due to the different masses, I'm guessing.
Okay, so let's start with the last question. When you buy a hammer or you get your hammer recalibrated, you may get more than one value. And that more than one value usually has to do with using the hammer with different tips. So like a hammer like this, you have a soft tip, you have a hard tip, and there will be a slightly different value of the sensitivity due to the mass of that tip and the compliance. So that's one thing. Or even some hammers, you can add a mass and have, we call it extended mass. And I think the little guy here comes with a little tiny mass I just saw.
Yes,
so you get different calibration values because of the different mass of the hammer and the different tips. The handle, the mini hammer has 2 handles. It has a solid handle because I guess, you expect the handle to be solid. But it's very hard to use the hammer because the hammer is so light and so small. So the flexible handle is this white handle here. If you can see on the camera, this handle is flexible. You can do like a slingshot. You can basically flex the handle and do like this. Boom. I don't know. Can you see on the camera?
Yes.
Oh yeah.
We use that.
Yeah. So I guess that's a way to, instead of moving my hand, and my hand is so
that's how it's
massive,
used.
it's easier. Instead of moving my hand, I hold the hammer with my hand and I just use the spring of the handle, the spring properties of the handle. So that's unique about this handle. The other thing is, yes, the handle of the hammer can influence on the measurement. The answer is yes. And if you go back to my presentation, let me go and share my screen again for a sec. If you go back to my presentation here, you will see that there is a patent which probably expired by now, but yeah. But you can Google US patent 4799375, and you can read that patent, and that's what is a tuned hammer. We call it a modally tuned hammer, where one of our engineers did a study on how to minimize. There was a resonance of the handle of the hammer, and that resonance caused a glitch on the excitation, and he figured out a way to measure that and just change the mass of the head of the hammer to minimize that problem. And it was a smart idea, and he wrote a patent on it. And you can read that. It's publicly available. It's an interesting, if you're curious about, you can read that. It's publicly available.
Is it correct to say that any mass on the back of the hammer is going to influence the calibration directly?
If you add a mass on the back of the hammer, yeah, it changes things, yes.
So, I mean, so the handle mass, the effective mass of the handle, how much is moving at the end, would also change the calibration?
Well, not as much. No, because the handle of the mass, is not in the direct line of the sensing. So,
well, some portion of it is swinging, tending to push the hammer forward. So that would intend to increase the force. But no, that shouldn't matter though, should it? I always get confused there.
But I think, the influence of the handle is minimum because it's not in the direction of the sensing, but there is some influence, and that's what that study showed, and that's how they worked on compensating for that. The added mass you put in the line of the measurement, that added mass will influence way more, and you can measure that during the calibration process. You can find that difference.
Colin?
And again, and most important, if you want to have a heavier mass, you don't need to buy a new hammer. So that's kind of an easy way to increase the amplitude of the heating when you're doing impact testing, which probably on a violin, you don't want to hammer it too hard, but if there are other applications where you may need an extra force or an extra oomph on the hammer.
For a cello, for example. But practically speaking, as Lucas said, you can put almost any handle on it and it'll measure about the same, which is liberating because
the original hammers, the original prototypes, you could go here at the University of Cincinnati, and some of the old professors there, that's how they made the first hammer. They took an existing sensor from PCB and just, they drew a tap, they tapped an existing hammer, and they made an instrumented hammer. Okay. And so like that whole relationship between Model Shop and Cincinnati and the professors here, that's how the hammer was invented, because some of those professors told PCB, say, hey, why don't you guys put a handle on the force sensor and make it an instrumented hammer? And that was back in the 70s, and one of those professors was the uncle of the founder of the Model Shop, and it was all in the family. In the PCB said, sure, that looks like a good idea, and PCB did that, and then told HP at the time, hey, we got this hammer thing, and HP said, great, we'll have this analyzer that does FFT. And that's how, companies have grown. I mean, our company went from, 20 people to what it is today by basically listening to people with good ideas. And of course, it's much easier to do that when you're a smaller company, but we still try to do that today, even being a much larger organization, trying to talk to you guys and listen to some of the good ideas you may have, which we may be able to do something together, maybe not. I don't know.
Okay,
Colin?
Colin?
Can I make a general point?
Yes, Colin.
The purpose of a hammer is to put energy into the vibrational modes of the violin.
Correct.
And those are the modes you want to actually measure. And it's not simply the force, it's the energy you put in. It's the integrated force and compliance and over time, the area underneath that curve. And in addition to the energy that's measured by the force hammer, you're actually putting energy into the hammer as well. And so that not all the energy that you might think that you measure from on the force is going into the violin. Some of it's going into the hammer. And I mean, if you look at the response of the hammer after the hammer, you can often see that. And particularly if you use the flexible hammer, you can actually see the vibrations of the shaft, as it were. And so you have to be a little bit careful about what exactly what was on measuring. And as you quite rightly say, I mean, the important thing is that you want as much energy transferred to the violin in a certain sense. But I mean, that means I mean, if you have two masses, the way to do that is to have equal masses of the hammer and the thing that the mass you're hitting. So only half in the impact, half of it goes into one, and the other one reverses it. Newton's cradle, for example, is an example of this sort of thing. And if you did it with masses of different masses, pendula of different masses, you actually see the rebound is different. And so only certain amounts of the energy that's going in to actually make eventually some of that energy goes into sound, some of it just simply goes into the non-vibrating structures of vibrating but non-radiating structures of the instrument. So there's all sorts of things that you have to worry about in designing the hammer instrument interaction.
But Colin, surely the some of the energy is going to leak out all over the place. But the important thing about the hammer is that all of the energy that goes into the violin is measured, and none of the other wasted energy is measured.
No. Action and reaction are equal and opposite, and the force that's acting on the violin is equal and opposite to the force that's acting on the hammer. So,
Yes,
so you don't want really to be worried about the energy that's going back into the hammer. And that's why the hammer design is very important.
But the energy that's going into the hammer, into the handle, it's not compressing the crystal, so it doesn't get into the equation.
Oh, yes, it is.
I mean, add a comment?
It excites all the modes of the hammer.
Yeah, let Jim.
Can I add a comment here? I think, Colin, you just said the most important thing about action and reaction being equal. What the hammer is not trying to measure energy, it's measuring force. The force is equal and opposite. So you have measured the actual force that's acting on the violin, regardless of the hammer handle or what happens afterwards. And so your transfer function should be correct.
Well, I'm not saying that your transfer function might not be correct, but it is actually putting energy in, because it's the integrated force times its velocity, that is actually putting the energy in.
That's true. The most important thing about the mass of the hammer and the handle and all that is how quickly the hammer rebounds.
Yes, I agree. I agree
the
about
bandwidth is determined by the mass, and that's why you want a lightweight hammer if you want to push to high frequencies.
Gentlemen, let me just intervene here.
Yeah.
And that's why, that's why when you design the hammer, you basically, you put the sensor right there at the tip. The only thing between the sensor and the structure is the tip, and we take that into consideration during the calibration process.
How much mass is between the
very little, but it depends on the hammer and the tip, but it's very little, but it does make a difference. And that's where if you just go back for a second on slide number, let's see. Yeah, so that's when I probably went too fast through this slide, but that's where you're measuring the force right here on the sensor, and then you have this the influence of the inertia of that tip on the mass, the mass tip, and then the force that's actually being applied on the structure, and that is taken into consideration when we do the calibration with the tip on it.
So
and of course,
so with the little hammer, it's that little last bit of tube with the point on it. And I know you can file away the point, because I talked to an engineer there and he said that shouldn't be a problem. So I would guess there's maybe a 50th of a gram or something between the.
Well, with the little hammer, I guess that the metal tip is almost integral to the sensor. It's like with the other hammers, you have little rubber tip or a nylon tip, and you can remove and just replace those tips. If I have a picture here, maybe. Yeah, you can see here when you got a red tip, you have a blue tip. You have those different tips that you can exchange. One is softer, one is harder, one is a medium soft. So those are some things you do. But either way, the assumption is, you're taking that into account. And when you look at the time domain response and the frequency response of the hammer, of the force sensor, you can see the differences. You can actually quantify that pulse duration and that amplitude of that pulse.
Okay, so Hans has a question.
Yes, I would just like to have your gentleman's opinion on reverse FFTs and deconvolution to reduce or just get rid of the effect of the hammer afterwards. Maybe Jim? Deconvolving the FFT?
I'm not quite sure where you're coming from. If you're measuring transfer functions, then you're already you're dividing by the FFT of the force input, and you're getting the thing you want without needing to do anything. If you want time histories, then the inverse FFT is of the transfer function. So the hammer shouldn't have any role in that, provided you haven't done anything silly.
Okay, I see. Yeah. I'm thinking just of the end result being a time domain. Anyway.
The critical thing there is nothing to do with any of the things that this discussion has been about, but is to do with the phase accuracy of your electronics. Especially if you're trying to push up to 8 or 10 kilohertz, there is usually some phase distortion. It's far worse with laser vibrometers than with accelerometers. There's a huge phase distortion. You have to compensate in software for the phase distortion in a laser vibrometer. The accelerometers are pretty good, although there's still probably a microsecond or two of processing delay in the actual output if you really try to get the phase properly calibrated.
at last something bad about the laser way because it's so expensive.
Oh yeah, no, it's very fiddly. It's great for not having added mass and for measuring velocity, so it gets to lower frequencies than an accelerometer, but it's hugely fiddly.
I just mentioned this. I'm sorry to, I don't want to disrupt the talk, but I just mentioned this because Patrick Attendees in Manchester has developed an algorithm to reduce or actually get rid of the effect of the hammer. But that is for producing time domain, results. I'm not quite qualified to explain the fine details of it, but I thought you might know.
I thought it'd be great to have Patrick on if he'd be game, because he's an expert in signal processing and real-time convolution.
All right, so that's a different subject. But I have a couple of questions for Marco. One is that with the your your DigiDAQ, yeah, that looks like a great little module. I mean, so congratulations on that. But is the ICP standard do other companies use it, or is it only your company uses that standard?
No, no. Well, ICP is really not a standard, but ICP is a trademark of PCB, and the generic name for ICP is IEPE.
Oh, okay.
And some people, depending who you talk to, some people call it constant current line drive or isotron, deltatron. There are many names out there in the market. The one name that everybody seems to agree on is ICP because PCB was kind of a pioneer in this technology. Because the sensors are piezoelectric, they really output a charge, and the way to handle a charge is to use a charge amplifier. Charge amplifiers are, you can think about it as a power supply, but they were very expensive. The electronics to design and build a power amplifier, a charge amplifier, it was very expensive. And so what PCB thought about it back in the day was like with the electronics available at the time, they said, why don't we put the charge amplifier inside the sensor, right, next to the crystal? So we just get the signal already amplified from the sensor. So that idea became extremely popular over the years. Because for many reasons. One reason was, hey, the signal is already amplified, so that allowed people to use long cables or not having to worry too much about cable noise and noise to the cable shaking, that kind of stuff. It drastically reduces the problems you would have with cables. You could use lower cost cables and not worry about noise as much. And the other thing that made life easier for putting the preamplifier inside the accelerometer was to make people that were making data acquisition, you could have you could use a constant current source using a constant current diode. And I apologize, I'm not an electronic guy, but it made it really easy for the electronics. You could embed that into your input channel in the data acquisition system. And so all in all, it made it very easy to use just a coaxial cable to connect the sensor to the data acquisition system. In terms of ICP, the way it works, the current that you supply to the sensor has to be anywhere from 2 milliamps to 20 milliamps. Some people use 4 milliamps, some people use 10 milliamps, some people use 2 milliamps. But in general, the sensor will work with any As long as that current is constant, within 2 and 20 milliamps, you will be able
So
to
the practical
power.
question I have is that other manufacturers, oh, wait a minute, you're all red. Oops.
Uh,
I don't know if Marco's
I'm
still with
what?
us.
Yeah, he's here.
I'm still with
We
you,
can
yes.
see him.
Oh, okay. Maybe I'm running into problems. My practical question is, are other manufacturers, i.e. PE sensors, compatible with your DigiDAQ?
Oh, yes,
Okay.
100%. So
All right.
so PCB did that back in the 70s, and then what happens is that, some people said, well, that's a good idea. Some people said, no, I think I know a way that's better. Instead of using constant current, some people try to use constant voltage. And anyway, a long story short, ICP became almost like a standard in the sound and vibration measurement community. And 80%, I would say 80% to 90% of the customers that we work with use ICP. But there's like many times where you cannot use ICP in applications that require, for example, high temperature. So then that electronics that we have inside the sensor won't work. It's limited on temperature. So some really high temperature applications, there are some restrictions you cannot use.
Mm-hmm.
And after ICP became popular with piezoelectric accelerometers, somebody said, "Well, can we make a microphone work with that same kind of electronics?" And that came a little later in the game, where they realized that pre-polarized microphones could work with an ICP preamplifier, and again, drastically simplify the electronics. And it became very popular in the performance of the sensors. You didn't lose much, or if you lost anything. So today, a lot of the sensors are ICP, not every sensor. And if you buy it from different manufacturers out there, they may call it a different name, but they work interchangeably.
Okay. So the next question I have, and I'm always confused by this, is whenever I look at a calibration microphone, and I look at those, they always talk about free field microphones versus non-free field microphones, and it's always incredibly confusing to me. Are they the same microphones?
They are the technology, the design is pretty much the same, right? But the way they work is the same. But it's just a matter of how flat is the microphone, because the microphone is not invisible, right? And when I say invisible, I'm thinking about the wavelength. So if you're measuring something that's high frequency, if you're measuring something that's low frequency, the wavelength of the sound is much, much larger than the size of the microphone. And pretty much the microphone becomes invisible to the sound field. But once you go higher and higher in frequency, the microphone becomes a big elephant in the room, right? If you're measuring a little tiny wavelength associated with a high frequency sound. And that's where the microphone starts to influence the sound field. So that's where the manufacturers of microphones and the people that wrote the standards back in the day, they understood that problem. And they realized, okay, well, if this microphone is going to be used in a free field condition, then we want to make it as flat as possible to the highest frequency. So when you buy a microphone, it says free field, they say, okay, you get this frequency response, and it's assuming that, you are maybe out there in the woods, right? There's no reflection. You don't have sound coming from all directions. You just have sound, you have sound coming from the source into the microphone, which is which is usually the most common situation, even though it's not a perfect situation always. But again, it all depends on the frequency. And again, if you had a microphone, like we talked about, the 1/8 of an inch microphone, that microphone is so small that will, technically speaking, that microphone would will work just fine in any sound field. But the downside of it, the trade-off is not very sensitive. That microphone is not very sensitive.
All right, just for someone in the audience, I'm just looking at a chart. So a 10 kilohertz wavelength is about a little over an inch. So, right, so that starts to become comparable to the size of the microphone capsule.
Well, in practice, when you do a calibration of a microphone, anything below 1,000 hertz, you're fine.
Yeah.
Right, when you start getting above a few thousand hertz, that's when you start to see a difference. This microphone is flat, but this is not flat.
So the differences are mainly in the higher frequencies. That's what you're saying, yeah.
Right, and the frequency, because the geometry is more or less the same, the size is standardized, so there is a correction. So a lot of the manufacturers, they will, if you ask,